Hello again. So let's take a look at these problems that you had problems with, and it looks like you understood most of the concepts because you got a lot of the problems correct, but some reason you were struggling with these. So let's just see, just going through those same types of steps, you might have just made small errors here and there, and we're somehow just missing it. And so number 16 says a manufacturer knows that their items have a normally distributed lifespan. So that's one of the big things, is the population is normal, with a mean of 6.3, so there's the mean, and a standard deviation, so sigma is 1.1. And if you randomly purchase 17 items, so that's our sample size, what is the probability that their mean lifespan will be longer than 7 years? So we're looking for what's the probability that the mean of the sample, not the mean of the population, because we know that's 6.3, but the sample, so x bar, is more than 7. So I put the greater than or equal to versus just a greater than. When we're talking about normal distributions, those are actually the same, because when it's continuous, it doesn't matter if we have including the boundary or not, it's going to give us the same area. So from the central limit theorem, the key thing here is it doesn't matter about our sample size not being 30, because since our population is normal, then we know the distribution of x bars of our sample means will be normal. What else does it tell us? We know that the mean of our population is also the mean of the sample mean. So we know right in the center of all of our x bars will be 6.3. And our standard deviation of these x bars, well, we can calculate that using the formula. This is just the population standard deviation divided by the square root of n, which is just 1.1 divided by square root of 17. And if we do this on a calculator very quickly, see, we get 1.1 divided by the square root of 17 gives us 0.2668 if we put 4 decimal places. So one thing about when you find these standard deviations, it's actually best if we don't round it at all. If you have if you can type this into your calculator, which StackCrunch allows on a computer but not on an iPad. But if we are rounding, then put a bunch of decimal places, because that rounding could change your probability. And in this case, I want to always put at least 4. So I'll put 0.2668. And there we go. So that's what our central limit theorem tells us, is that our distribution we're going to use to find the probability is normal with this mean and that standard deviation. And now we can find what's the probability of getting something that's higher than 7. So we're finding this area, this probability. So now it's just a matter of plugging it into our calculator. So I'll go over to StatCrunch. This is under Stat, Calculators, Normal. Put in our mean, which was 6.3. And our standard deviation was 0.2668. And we want to be greater than or equal to 7. Compute, and here we go. 0.0043 was our answer. So this probability here, which is our answer, is 0.0043. For number 18, it's the same exact idea to start off with. We have a normal distribution, a mean of 11 years, 11.1 years. And we have a standard deviation of 2.9. This time our n is 20. And it says, though, this time, it gives us 2% of the time their mean life will be less than how many years. So we're going to set it up the way we did the last one, but this time we're not looking for the probability. They already gave us the probability or percentage. They told us, oh, 2% of the time will be less than what boundary. So we're trying to figure out what's the boundary, right? How many years? That's the boundary we're looking for. Then also make sure we pay attention to this. It does say round it to our final answer to 1 decimal place, but make sure our individual or our intermediate steps don't round it to 1 decimal place, only the final answer. So in any case, doing the same exact thing we did before, since our population is normally distributed, we know the means are going to be normally distributed. And also the center of this is the mean of the population. And our standard deviation of our means is going to be 2.9 over the square root of 20, which gives us 0.6485. And now we're trying to figure out, again, what's the boundary where 2% of their life will be less than so many years. So 2% is a very small percentage. So the area to the left, since they're talking about less than, right, that's the area to the left, we're trying to figure out what is this boundary? What does this mean that's going to cut off 2%? So going back to our calculator, StatCrunch is going to give us this answer, right? In a sense, basically we're trying to figure out what does this mean? What is this boundary, this unknown variable here, that when I find the probability of getting less than it, it's 0.02. So going into StatCrunch, we just need to put in the 0.02 on the right side, and it'll fill in the boundary on the left side here inside the probability statement. So I go over to StatCrunch, see our mean was 11.1, our standard deviation after doing the calculation was 0.6485, and we want to be less than and figure out what is this boundary. So I don't want to put anything here, but I do know that the area should become 0.02. And there we go, 9.768. And if we're rounding to one decimal place as it says, that would be 9.8. So this X bar right here would be 9.8. And if we cut it off at 9.8, it'll cut off 2%. Number 20. On a distant planet, Cowabunga, the weights of cows have a normal distribution of a mean of 324 and a standard deviation of 29. So there's our population mean, population standard deviation. And again, we know they're normally distributed. So despite not having a sample size greater than 30, we can still use the normal distribution of means. And then it says it holds a maximum weight of 5848. So if 17 counts are randomly selected, and what is the probability of their total weight being over a maximum allowed of 5848? Well, if you think about this, the total weight is going to be above 5848, which means the mean weight, which is adding them all up to get the total divided by 17. It gives us this hint here is that, okay, this is the same thing as finding the probability of getting a mean. So this is where our central limit theorem comes in again, a mean greater than 344. Right? Because we're basically taking 5848 divided by the 17 cows, and we get a mean weight of 344. So they're asking, though, what is the probability that our mean weight is greater than 344? So going through the exact same process we did in the other two, since it's normally distributed, then the means are normally distributed. That's the central limit theorem. The center is going to be the population mean, and the standard deviation is going to be 29 over the square root of 17. And this will give us 7.0335. And now we can find what's the probability that we're going to be over 344. So 344 is somewhere like right here, and over would be the right side, greater than. And we're just trying to find that area, that probability. So this would just be going to StatCrunch again. Mean weight is 324. Standard deviation is 7.0335. And again, we're being greater than 344. And we get 0.0022. So this area here is 0.0022. And the last problem you struggled with was the proportion one. So here we're talking about proportions, categorical variables. And so it says in an election, suppose that 45% of voters support creating a new fire district. So this would be P, the proportion of the population who support this. And if we poll 97 of these voters, so our sample size is 97, the probability distribution for the proportion of the polled voters that support creating a new fire district can be modeled by the normal distribution picture below. So I didn't copy that, but let's just redraw it. So it had this where we needed to figure out what's the center, and we also needed to figure out what was 2 standard deviations away. Normally we go 3 in each direction, but here I just wanted the center and 2 away from in each direction. So it says the bell curve represents the distribution, and on the horizontal scale axis is the standard deviation of the sampling distribution. So each tick mark represents one standard deviation. So this was a tick mark, and then another one is what we're trying to fill in. And the middle tick mark is the mean. And so we just need to fill these boxes in. So it's just about, again, figuring out our mean, figuring out our standard deviation, and then calculating each of these points. So the formulas for proportions is if I'm looking at the sampling distribution of proportions, the mean of our p-hats, that's a sample proportion since we're taking a sample of 97, the formula is just p, right? It's just the same proportion as our population, right? We expect our samples to fall somewhere near where the population is going to be. So right in the center, our p is going to be 0.45. So right in the center is 0.45. Now to find these other two boxes, we just need to find our standard deviation. So the standard deviation of p hat, according to our formula, is actually the standard deviation, is actually the square root of p times q over n. So what is q? Remember, q is just equal to 1 minus p. It's the complement. It's what's the probability of failure. So there's a 45% chance someone supports it. That means there's a 1 minus 0.45 chance, or a 55% chance that they don't support it. So that's our q that we're going to use. And so filling in this formula is just going to be the square root of 0.45 times 0.55 divided by the square, divided by n, which they found is 97, since our sample size is 97. And again, we just type this into our calculator. So in this case, I have 0.45 times 0.55 divided by 97. Take the square root of that whole thing, and I get 0505. So how do we get these values here? Well, this is the size of one standard deviation, but the boxes we want to fill in are 2 standard deviations above and below. So we can just go up by 2 standard deviation, or add it twice. So 0.45 plus 2 standard deviations, or 0.0505 twice. And if we go up that amount, we get 0.551. And then if we go down 2 standard deviations to get the lower box over here, this is going to be go down twice the standard deviation size. That's 0.45 minus twice of the 0.05, and I get 0.349. And so there we go. This is 0.551 and 0.349, but if we were rounding the 2 decimal places, this would be 0.55, and this one would be 0.35.